calories, right? So a kilometer is, I think you talked about it. Yeah. A pound kilometer basically allows us to sit there and measure the energy that's going to be produced by something that's going to be able to produce large amount of energy, like a bomb, right? So the idea is that you can put a small size combustion type reaction in there and be able to sit there and determine how much energy is being generated from the heat that you're making. Okay, so this is an example of a bomb kilometer. Now we don't have one in lab. It's one of my goals. One of my dreams is to get a bomb kilometer. It'd be a lot of fun to, make many bombs. How much do they cost? This one, well, it's dated right now. It's hard to tell, but this is kind of like the older instrument. Some of the newer ones are going to cost you about $100K.
Oh, okay.
So upper end is $100K. We can get one for about $25K. So if you want to donate,
I don't have 25K.
But hey, if you do, what you do, you can start doing it. Okay, so now the way it works is it's going to be similar to a general kilometer, right? So a kilometer basically is going to have a thermometer, in this case, a precise thermometer. We're going to have inlet so that we can have oxygen in our system, because we know that every combustion type reaction is going to need what? It's going to need oxygen. So, and then this here is considered the bomb. So the reaction here is going to be in that sample plate. And then on the outside here, so the bomb is actually, it's basically a fortified steel type of situation. So it's surrounded by like hard, metal, something that's pretty strong, but it's going to be melted really easily by the heat that's being generated. And then on the outside, you have water. And you'll notice that the precision thermometer is in the water. So you're looking at the heat transfer that's actually occurring. Okay, it's a very simple instrument if you think about it, but it costs a lot of money, right? Because you're basically using high quality metal to make sure that it doesn't melt. So there's also whole body kilometers. So a lot of dietitians basically use this to determine whether or not you're metabolizing appropriately. So you guys are familiar with the calorie, right? We talked about the different, that's capital C calorie, small c calorie, right? Okay, so capital C calorie are food calories. Small c calories are normally what we decide. We talk about these, right? You guys remember? What are small c calories?
I was also not here, so I don't know.
Roll here. Anybody know? Well, we know the difference between capital C calories. Capital C calories are 1,000 small c calories, right? So, but we also know that a small c calorie is just basically how much energy it takes to go for 1 degree, that's right, of water, 1 gram of water, 1 degree temperature. And that's either Kelvin or Celsius. So when we talk about those food calories, we eat quite a bit, right? Here's the macaroni and cheese. And so if we take a look at our macaroni and cheese, this tells us our serving size, right? We always start here. And this tells us how many calories per serving size. Now you'll notice they actually use capital C calorie. So they let us know that, hey, this is really capital C calories. And there's a little bit of history. The reason why it was done, somebody had made a mistake when they were doing calculations, and it stayed that way. Plus, people don't want to hear that they're eating 250,000 calories, right? That's a lot of calories, right? Because you're, oh my God, how much that's right? And now you're really thinking you're going, right? So
They should have left it like that.
what was that?
They should have left it like that.
Okay, so that brings us to enthalpy. Now, enthalpy is another form of heat. We'll talk about it, but it's typically the heat that's associated with reactions or phase changes, right? So for instance, have you guys ever looked at like when water is like you're going from a freezing point to a thaw point? Anybody lived in where there was snow, a lot of snow? Yeah, you guys don't have this experience. Well, we live in it, so you guys know what it is. So you have, right? You have, okay. So you notice like when things are thawing, right? still see ice, even though the temperature's above that 4 degrees Celsius, right? And so like kind of like in our water, if we stick a thing of ice in the refrigerator, it'll stay water, right? Why? Why doesn't it just instantly melt? I mean, over time, if we leave it long enough at that level, what's that? It'll melt. So, but if I left it exactly at 0, 0 is freezing, right? So if I go like just slightly above, like 0.1 degrees Celsius, so you're gonna melt.
It'll slowly start.
Yeah, it'll take it a very long time. Okay, so part of the reason why that's the case is because of enthalpy. So it's kind of like that energy just to get it started, right? You need that energy just to get it up there, right? So to get it to the point where it's going to melt, you need a little bit more to get it over there. So when we think about enthalpy, or just in terms of phase change, and I'll turn on this. Where's Stephanie? She's supposed to yell at me. I forgot this, right? Sorry. I feel like it's been a while since we used the screen here. Okay, so this is kind of like what we call an energy temperature, right? So this plateau, right? This is like how much energy that we basically need to get over the hump. This here would represent our input. Okay. Delta H is a symbol for input.
Thank you.
So this is your delta H. And so it's just like how much more energy that we need to get over. This here would be our Q. That would just represent the heat. So that curve coming up would represent Q. If you guys remember, Q equals what? Q equals heat, but what is the formula? M, yeah, M, C delta T. Okay, so Q equals MC delta T, where we would go basically from the negative value to 0, and then this will be the enthalpy of freezing, right? And there's a value that's associated with that. And then this would be, and this would be Q of ice, or let's say Q of ice, C of ice. So this here would be Q water. And then that would basically go from 0 to 100. And then you have another enthalpy associated with the transition from liquid to gas. Evaporation. And then you also have a Q that's associated with gas. Okay. So this plateau, when we get to that plateau, like when we get exactly at zero, if you don't put enough energy into it, you're not gonna get out of freezing. It'll stay frozen, right? Because we know that it freezes at zero, but it doesn't, you need that hump to get over from freezing to thawing, right? So to get up to that next degree, we're gonna have to put some more energy in, more than what it takes, okay? And so this is the energy that's going to be associated with that phase change from ice to liquid. Now, all solids are going to have this property, right? You always are going to need that enthalpy that's going to associate with that. Okay? You guys kind of understand that? Okay, you guys have that look. Does that look like what the fuck is he talking about, right? Okay. So when we talk about enthalpy, enthalpy is going to be associated with energy. It's that energy. And so usually it's the energy of a reaction, or like I said, a change, a phase change, right? Okay, so if we're going from a solid to a liquid, it takes energy to make that happen. And it's like a threshold. If you don't put enough into it, right, then you're not going to be able to get to that next stage. Okay, not only putting that temperature in, like that temperature change, you need to make sure that you give enough energy to get over the hump. Okay, so if we think about it, if we're looking at all of the energy to go from ice to a gas, we have to take in consideration all of these different stages that are happening. Okay, so if we're looking at the energy total, Q total is going to equal Q ice plus delta H fusion plus Q water plus delta H evaporation plus Q gas. So we're getting all of the energy that's going to be needed to go from -10 to 20 degrees Celsius. Okay. Is that clear?
What is that?
What's it at? Let's read it. Oh, yeah, there it is. Okay, 7. You don't know what to put for what? Their notes?
Oh, well, I'm writing those down too, but like this thing is like bothering me.
Oh, you guys just
I
passed.
don't know.
You were talking about important stuff, not you know.
Not chemistry.
Oh, never mind.
Can I what?
No, I was gonna say you can look, but I stopped there.
Oh, you're saying my head's in the way. Actually, your head is too big. It's in the way. It's okay. I can handle it. I already know I had a big head. So. Goes with the big brain.
Yeah, there you go. See?
So I needed I've taken an aside, a quick aside. So I know some of you are currently in Physics 2B. If you guys know anybody who needs to take Physics 2B next semester, please give them my email, right? I am working on making it happen, but it's not definite yet. I'm working on it still. I'm working on it. Actually, I'm gonna have to say, you have to open it up. You have to put it on the schedule so that we can, but he's gonna cancel if I don't get enough people. So that's what he says. Not doing it. But we're trying to find another way of doing it. We're looking for money. So
But it's not available still on the.
yeah, it's not available yet. We're working on it. They canceled 4A, but I'm like, hey, you canceled 4A and it's on Pathway. So they beat that chip. So if you know anybody who needs 4B, what was that? 4B. Yeah, I mean 2B, not 4B, 2B, Physics 2B. Anybody at all? Let them know. You need 2B? It's good,
Something
'cause
very
that's
important.
one more. So now I should get 5 more. 5 more. 5 more people. Right now you have 8 in the class, 9 in the class. We're gonna say 9, right? We're saying 9, and now we're saying 10, right? And then so I need 5 more. I need to try to get 15. I told him, I said, I get this, make it happen. We'll see. And I'm like, well, but I need a place to put them. That's my next thing. So okay, everybody got this? Did you guys get it? Okay, good. Okay, so the very first law of thermodynamics basically deals with energy is going to be conserved, right? And that's something that you're going to see throughout everything. Now, because of that, we're basically saying that the internal energy, U represents the internal energy. We're looking at delta U. Now, the reason why we're looking at delta U is because we can't just find a value for U. We have to look at the change that's occurring, okay? Because we're limited by our perspective. Okay? So delta U is going to equal Q plus W, where W represents the work, Q represents the heat. So if we ever think about in terms of a reaction, it's looking at the work that's being done as well as the heat that's being generated. Okay. So how many of you guys drive cars? How many know anything about cars? Excellent. You guys are experts here.
Uh-huh.
So the engine, how does the engine work? The gasoline.
Compression and spark.
So you said compression and spark. Okay. What's happening with that compression? Tell me how that works. It makes an explosion. Okay. And that explosion does what? It moves the pistons, right? So then that explosion also makes what's happening, what causes those pistons to be pushed up. Does it make this push up, push down? Yeah, that works, right? Am I wrong? You can correct me.
That's right.
That's right. Okay, so what's happening? What is happening to cause those pistons? You said explosion. What is that explosion generating?
Energy. Power.
It's generating heat, one of them. What else? Work, yes, work. But how is it generating work? Because we know that a piston cylinder is only so big, right?
Yeah.
It has a what associated with it? If the cylinder, we're talking about the cylinder, it has a what? What type of unit? What do we usually do?
Pressure tester.
What was that?
Pressure.
So yes, we're using pressure, but it also has that volume, right?
Oh, yeah.
Okay, because there's so much pressure being generated in that volume, that is going to be our work. So when we think about work, particularly in chemistry, we're thinking about pressure and that volume that it's in. Okay, so that's going to be our work. So pressure times volume is going to represent the work that's being done. And of course, heat, right? If it don't get hot, it ain't working, right? Because have you guys ever touched an engine?
Yes.
I have many times. Woo, right? Got out, I'm like, oh, I'm gonna be smart. I'm gonna take the oil cap off, right? And then as the oil shoots up and all that stuff, right? So I've done it all before. I have some of the marks to show for it,
So like,
Okay, so when we talk about that internal energy, okay, we're going to be talking about when that internal energy increases. When that internal energy increases, that's going to mean one of two things, right? One of those things is that the energy is being absorbed. The heat is being absorbed. So then we're going to have positive values, plus values, right? Or it's going to mean that the work on the system is going to be done. Sorry, the work on the surroundings is doing work on the system. Okay, and that also is going to be a positive value. Okay, so those are one of the two cases. So if we have a positive U, that basically means that either your Q is going to be positive or your work is going to be positive. Okay, either heat is going to be absorbed or heat is going to be, or work is being done. Surrounding is doing work on the system. Okay, I've got to define what the system is. You guys are probably saying, what the hell are you talking about the system? Right? So, yes.
It's, the heat, they both have to be the same, height, or they have to be.
Okay, so that's going to be really important, right? So, if we were thinking about it, right? So, if we're looking at a system as a whole, it has to equal 0, right? System as a whole. But if we're looking at just one aspect, right? And we're saying that the internal energy, just this aspect of the internal energy of this part of the system, right? Then it could be a positive. So if it's positive, it has two ways of being positive. Well, three ways. Okay. It could be positive if the heat is positive, or it could be positive if the work is positive. Right? If the other one's negative, right? As long as it's not big enough to overcome the other one, then it's okay. It's going to be positive. Does that make sense? Right? Or it could be the case where they're both positive. Okay, where your work and your heat are positive.
But like, I think that's like, are they always gonna both be positive, or
No.
like, can one be positive and negative?
No, they're not always going to. It just depends on the system as a whole. Yeah. And so, a lot of times, what we do, we look at one aspect of the system. We don't look at the other aspect. And we know that by looking at this one aspect of the system, the other aspect of the system has to balance it out, because we know that in terms of energy being transferred, right, it has to be 0. It has to add up to 0.
So you said it'll be a positive value if like energy is being absorbed,
Yes. So if heat was, if
or
it's
work
being,
is
yeah,
being done
yeah, that's right. Work is being done on the system.
on the system.
So let me give you kind of perspective, because it's all about perspective. Well, I'll show you the slide here in a second. So let me tell you the other hand, right? So the internal energy is going to decrease, right, when heat is being released. So exothermic, just, or the system does work on the surroundings. Okay, so earlier we had the surroundings doing work on the system. Here we have system doing work on the surroundings. We didn't get a copy.
this whole side.
I didn't like any of you guys. Sorry.
Wow.
It's not a. No,
Anybody over here?
no, it's just over here. Just over here.
Yeah.
I really don't like it.
No, you can check if there's like something
I like
Okay, so when we look at it, this here represents the system. This here is our surroundings. Okay, so if the system is releasing heat, right, then our delta U is going to be less than 0. Right? So that basically means that the system is releasing heat into the surroundings. It's going to be a negative value, which makes sense. It's releasing, right? Because that's on the other side of the reaction.
Delta
Okay.
U stands for internal energy.
That's right. And then, or we could have the case where work is being done. So work is being done by the system on the surroundings. Okay. So in that case, that internal energy is going to be 0, right? Or less than 0. So the internal energy is going to be greater than 0 when the surrounding is, or heat is being absorbed by the system. Or work is being done on the system by the surroundings. So if we think about, again, that gas engine, what's happening in that case? Sure. You said work is being done by the system. That's right. Work is being done by the system, and what else is happening? It's actually that heat is also going out. That touch it, right? Is it cold or is it hot? When the engine is really running, right? It's hot. Touch your engine after you just used it, right? No, don't touch it, right? Don't touch it. Dr. Henry told me to. Now, I'm learning as you're in the hospital, right? You know. I was doing chemistry and I
Listen, it's fine, it was for science.
okay, so now this kind of makes sense now. Now that you're talking about that compression and expansion, right? It says expansion work, right? Expansion work is just that pressure or that work that we do, right? Because it's expanding. It's causing that, you know, the piston to push out because it's expanding, right? Expanding. Okay. So, we already talked about the combustion engine. Okay, so we've already kind of talked about this in this case. So we already know that this is going to be exothermic, right? And we also know that the piston is going to be pushed out, right? So in both cases, those values are going to be negative values, right? And so that means our energies are going to be, our delta U is going to decrease or increase. Decrease. It also says at the bottom, right? So good. I'm glad you guys are reading. It makes me feel good. Now I'm going to tell you a secret, right? I usually find out that most people don't even read any of the slides, even though they'll put the answers right up there. I did that on a test for one of my classes. Had the answers. 2 of the answers were right on the board, right? Left it up the whole time. I only had 4 out of, I had 2 classes that day. 4 out of 40 students get it right.
Was it one I had too, right?
What was that?
Is that why you have to go,
Is that why I had to?
why you have to cut your?
Yeah, that was part of that reason, yes. Long story, yes, I was really mad about it, yes. Anyway, state functions, okay? So we kind of talked, did we talk about state functions? We talked about the mountain? We haven't talked about the mountain? Okay. well, we're talking about that. Okay, so a state function, first off, let me say, internal energy is a state function, okay? Now, I want you guys to sit there and think about it, right? Let's say we're climbing a mountain, right? So in this case, we're gonna be climbing Mount Kilimanjaro, right? Okay, so we have a couple ways to climb Mount Kilimanjaro, right? And you know, depending on who you are, how much in shape you are, what you want to do, there's a couple ways of getting up that mountain, right? One of them is going straight up the mountain, right? Straight, because that's the shortest distance possible, right? Most people who are really super fit, they're probably going to be the ones, oh yeah, I want to challenge. Let's go, right? You know, those are the ones that are going to do that. The ones that, you know what I'm talking about. Exactly.
Right.
Yeah, we got it over there. Right? Okay, so, and then we have the ones that are like, okay, you know what? We're just going to take that path, right? You know, the path that's already kind of carved out. Yeah. And then there's gonna be people like me that said, fuck that, I'm just gonna get a helicopter and go from the helicopter there, right? All three ways gets us to Mount Kilimanjaro. All three ways technically take the same amount of energy. Technically, right? Because either I'm using energy from gas to sit there and get me up there. He's using, brute force energy, right? And then you guys are using, same way. If you add up that path, it adds up to the same amount of energy. Okay? So state functions, basically, no matter how you go, should add up to the same thing at the end. Right? Okay? So this is just basically showing you that. If I go this way, if I go this way, at the end of the day, it's going to add up to the same amount of energy. Okay? Okay, so that's going to be important. Keep it in mind. Keep it in mind. Well, enthalpy is also a state function. Okay? We know that delta U is a state function. Enthalpy is also a state function. Okay, so because we can't measure enthalpy directly, we always have to measure the change. Okay, for chemical and physical processes. So we're always looking at delta H. So we have to change our equation, right? Since we're looking at that change. So then we say delta H is going to equal delta U plus P. In this case, in chemistry, we're saying P is always constant, right? Because it's always atmospheric pressure. Everything that we do are pretty much exposed to the atmosphere. Okay? The thing that we're changing, the things that we can control, is basically all. Right? So delta H is equal to delta U plus P delta V. Now we already know that P delta V is going to equal, in this case, negative work. Negative. Yeah. So in this case, if we think about it, now negative work would suggest that what is being done is the system doing work on the, is the surroundings doing work on the system, or is the system doing work on the surroundings? So if we're doing a chemical reaction, what's going to happen?
The latter.
Yeah, that's why we get that. Okay, so if we go ahead and substitute things in, right? So for delta H, we're going to just call this QP, and then we plug this in. So in other words, we get delta H is going to be QP plus W minus W, and then we end up with delta H is just going to equal QP, where Q is going to be the pressure at constant pressure. The heat at constant pressure. Okay, in other words, the heat at constant pressure is just going to equal delta H. Okay, so because of that, we have this whole table that is dedicated to delta H values at standard temperature pressure, or constant pressure. Okay, and this is an example of that. So we have a chemical reaction here where you have a hydrogen gas and oxygen gas instead of water. Okay, so when we look at this, and let me make a correction. This should actually be joules per mole. So anytime that you guys see delta H should be in joules per mole. Okay, because it's going to be based upon 1 mole of substance, right? So in this case, it's going to be based upon 1 mole of water because it's being solved for 1 mole of water. So if you look at the chemical equation, remember when we were balancing chemical equations, I told you, you can't have a half of a molecule, right? Here we're looking at the context of having molar, right? It's not a particulate, it's not on that atom to atom level. We're talking about a whole bunch. So in this case, we're talking about them. So that's why we have to put it in terms of per mole. So in other words, this value, our delta H, is a negative value. That basically means that energy is going to be released. That means that it's going to be on the product side, right? If it's negative, it's on the product side. If it's positive, it's gonna be on the reactant side. So if it's positive, we're adding energy into the system. If it's negative, energy is being released from the system. Got that?
Yes, sir.
What did I say?
If it's adding to the system, it's a positive, it's going away or contracting. It's negative, right?
That's right. If it's being released.
There you go.
Okay,
That's where-
so we know that if it's endothermic, it's gonna be what value?
Positive.
Positive. It's exothermic, it's gonna be negative. Okay? So in this case, is this an endothermic reaction or is this an exothermic reaction? Okay, now, but you'll notice, yeah, you got that half, right? Okay, again, because we're making it reference to water. So in other words, for every 1 mole of water, this is how much energy is involved. Okay, so I can calculate if I have 50 moles of water, how much energy would that be? We multiply this by 50, right? So that's why it's technically kilojoules per mole.
100%.
Yes.
So like if you know that that's normal, you can't plug in like 50 variable and then like,
Yeah, you would start off, you would do it the same way that you do any chemical reaction, right? It's based upon mole, everything is balanced. So then you know if we're talking about water, right? So we know that we have this.
Appreciate it.
No problem. I can erase it, so everybody got this down.
Yeah.
So if I have 50 moles of water. Based on that equation, for every 1 mole of water, that's it. In this case, negative 287, 286. 286.
Yeah.
Okay, and that's per 1 mole of water. So then, well, and then that would give me how much energy.
Oh.
Okay. Does that make sense?
I want to say yes, but
No?
No.
Okay, well, that's all right.
I don't know
So,
what the kilojoule.
because if we go back to the chemical equation, you guys are back on the chemical equation, right?
This is-
Yeah, that thing right there. Yes. Yes.
Yeah.
You see it?
I'm on the correct page.
Okay, you're on the correct page. That's good. So, since we know that that is per mole, per 1 mole of water, right? It's based upon 1 mole of water. How many moles are in front of, what is the coefficient in front of the water? On that chemical equation, on the chemical equation. It's 1, right? Because let me write the chemical equation so we can put it together. So we have H2.
I know.
As we have it set up, so it's 1, yes.
So I apologize for interrupting you after writing everything down. I understand what's being said here. I don't understand what kilojoules are.
You missed the lecture on kilojoules.
I believe I did.
Kilojoules is just energy. Okay, Jay? It's a form of energy. So what it really means is, as an example. No, stay right where you're at. Stay right where you're at.
Did I put my feet up?
No, yeah, put your feet up. So if I decide to push you a meter, right? A meter. So it's the amount of force, right, that it's taking to push you a meter, or amount of technically energy. Force that it takes you to push a meter in distance, right? So that is going to represent what a kilojoule is. So it's that energy that's taking to push you that far. That is going to be a kilojoule, or that's going to be a joule. Okay, 1 joule is going to be that. Now, a kilojoule is 1,000 times more. So joules is what they use for SI units. So it's the energy that's associated with that force that's being done. Okay, that 1 meter. Okay, does that make sense?
Yeah.
Okay.
So that does make sense.
Okay, so that's what a joule is. And so if we think about heat in this context, right? So we, in the US, we do it in terms of calorie, that change in temperature as a result of that, right? So we can sit there and think about how much heat is being generated to do that push, how much, and so then we can kind of convert it in that sense. And so that would be the direct correlation to that. Does that make sense? And so they know that for 1 joule, that's going to be equal to 4.184 calories. No, sorry. 1 calorie is equal to 4.184 joules. If you look back at the lecture, it actually shows you that.
No, I forgot. Yeah, right.
Okay, does that help you guys?
Yes.
Okay. Okay. So now, since delta H is also going to be an extensive property, right? So that basically means that we have to multiply the number of moles that we have by that number. Okay. So in that context, to do that, if we multiply that, that's also going to be multiplying, say, 2 times 50. Okay. So then that we just multiply it by that energy. Does that make sense? So in other words, it's going to be dependent on how much you have, right? So if you only have a little bit, are you going to get a lot? Okay, we're lighting up something, right? We're trying to burn down this room, right? Or we want this room to be really, really hot, right? And then I said, okay, I want this room to be really, really hot. And I bring a cup of gasoline, a little cup of gasoline. Is that going to make this room really, really hot? No, it isn't, right? So if I want to make this room really, really hot, I'm going to have to bring a lot more gasoline, right? Does that make sense? That's what we're basically saying, right? The more you have, the more energy you're going to have.
Gas lines.
You got to be creative. So if we really want to burn it, I'll keep that in mind. When I want to burn down the building, I'll let you know. We'll have you come in and be creative. Okay?
It'll be pretty effective. I mean, there's those sprinklers in
That's true. And we know that this stuff burns. Okay.
Joe speakers over sprinklers.
So the other thing that I want to stress is that you have to pay attention to the physical state of things, right? That's going to be very important because gas and liquids are different, right? Aren't they? Gas, liquids, and solids, they're different. We can all agree to that, right? Yeah. Okay, because they're different, it's going to take us a little more energy to make things happen, right? In certain states. And so in other words, if we're going from the liquid, we're going to have more energy that's going to be released in that situation from those 2 gases. If we're going to the gas, it's less energy because it's already in that state, right? Does that make sense?
Referring to like how the particles are moving?
Yeah. Yes, exactly, yes. Okay, so we already talked about positive and negative, right? So we know that it's going to be negative. If our delta H is negative, it's going to be endothermic or exothermic. Exo. And we know that if it's positive, it's going to be endo. Okay. And so this is just basically showing. Okay, now here's the secret, right? You notice what did they do about these reactions? It's the same reaction. What did they do with it? What is the distinction between them? They're flipped, right?
Yeah.
So the bottom one's flipped. Okay, it's also flipped inside. This is something that you guys need to know, right? So every reaction technically can go both ways, right? So that means we can flip it in one case. If this case, we're gonna have to put in this energy, this amount of energy, okay, to make it happen. In this case, we get this amount of energy released. So to make it happen, we're gonna have to add this amount of energy to that water to make these 2 happen. make it to produce that. In this case, we're gonna have to release that amount of energy. That's how much energy is gonna be released.
Every reaction is equal or opposite.
Yes. That is, yes, Newton's law.
Yeah.
Yes. Yes, in a sense, yes. This,
So this
it
is
kind of
the
deals with it.
case.
Yes, in a sense, it does. In a sense. Now, there's some other things that we have to add on to it because there's a little bit more to it. And that deals with order and chaos, right? And so things will happen under certain circumstances. Things will be ordered, it's not gonna happen. If it's chaotic, oh, it's gonna happen spontaneously. Okay, we'll talk about that a little bit later, but for right now, this is the case. Okay, so you guys already did the gummy bear reaction, right?
Yeah.
Okay, so this is a piece of cake. So some of those calculations that we're talking about. Okay, so a gummy bear contains 2.67 grams of sucrose. Sucrose is C12H22O11. When the gummy bear reacts with 7.19 grams of potassium chlorate, KClO3, 43.7 kilojoules of heat is produced. Determine the enthalpy change from the following reaction. While you guys read it, I'm going to write all of the Greek on the boards. So I'm going to say generally, since you guys are working this out. Generally, if we're looking at this, the first thing that you guys should think about, right, other than this being an enthalpy reaction, you should think about something. What is that? Something that we should be thinking. Look at what you're given.
For units.
Not just the units.
Molar mass.
Molar mass. All that's important. Everything you're saying is important, but there's something that should be like red flags. Flags should be popping up like crazy.
The coefficient.
No, not the coefficients. What's good?
Everything.
The grams of potassium chlorate and sucrose.
Okay, so what do we know about this? What side of the reaction?
Reactants?
Yeah, reactants.
They're both reactants. So what happens if we have two reactants? What is that? First thing that we should probably be thinking. What?
No.
You're just want to blow shit up, aren't you? You're gonna burn to the ground. You know, it's like,
If it's endothermic or exothermic.
The total weight,
that?
the total weight,
No.
Dr. Henry, give us a stick, something, give us a carrot.
You want me to give you a stick? You want me to give you a carrot?
Carrot on
You
the
want a
stick,
stick or a carrot?
either one.
Either one. Give me something. Give me something. I'll give you a hint.
No.
Last chapter, the very last part of last chapter, we talked about cheese sandwiches. That's right. So we know as soon as you see that there are two reactants that are given to you, the first thing that should pop in your mind is that, oh shit, this is one of those long ass problems, right? And you should correct yourself for it, right? Because you guys know that they're long problems, right? Are they not? Yeah, everybody said, yeah, right? So we know that we have a limiting reactants problem. So that's how we're going to start, right? Thinking that. Said you wanted a stick. I gave, was that big enough stick for you?
I think that was too big of a stick. I don't know what to tell you.
You got real all of a sudden, right? We don't even work you guys through it easily. We just push you in, right?
Unfortunately.
we need some molar masses. So we have 12 times. Who's checking my math for? 12 times 12.
64. Oh, shit.
Yeah, 22 times 1. And we have 11 times 60.
Wait, no, I have 187? No, that sounds wrong.
It is wrong.
The thing is, it sounds wrong. So. 176. There you go. I was off.
Okay, so we have these two together. Mole. So we have the molar mass. We know that we have grams, we have to change it to moles. We do that by using the molar mass. So is that going to go on top or the bottom? So that grams going to go on top or on the bottom?
Up on.
Okay, so we have 342 grams on the bottom, 1 on top, and that's all C of H2. 11. 11. Okay.
Dr. Hunter, did you mention that C11, like 11 carbon, not moles?
Oh, I was supposed to be, my bad. I just worked on it. Well, the other,
Yeah.
well. Yeah, it's the brain part. So. Anybody doing that heavy lifting for me? On potassium weighs. So I'm gonna just be lazy. And CL.
35.
And then, yeah, 3 oxygens. Together. Everybody see? Doesn't look good if you just plug it in, but or let mine read. Yeah.
0587. 87.
Okay, so we need to figure out which one's limiting, right? There's a couple ways that we can do it. We could just do some willy-nilly reaction and just try to figure out the other side. Or what we can do is just figure out by changing these moles to moles of sucrose. And so how would I do that? I have 0.0587 moles of potassium chloride. How do I figure out how many moles of sucrose I need to react? What was that? With the equation, the chemical equation. So I'm going to use the equation. Right? So for every 8 moles of potassium chloride I have how many moles of sucrose? Yes. Okay, so which one is limiting? Sucrose. This is what we need to react. Potassium. And then this is what we have. So which one's limiting? So potassium chloride is going to be limiting, right? Because we have more than enough to actually react. So this is the excess. So we would take these moles. We have these moles. And 0. I write tiny there. So I have 0.087 moles of potassium. Okay, so we're already ahead of the game, right? So we already have this in moles of sucrose, right? How much sucrose we be making. So then what we're gonna do is, we know that delta H. Delta H equals a Q over moles. Okay. So then all we have to do is get our answer for our delta H. Delta H is going to equal, it's going to be moles, in this case, the sucrose. So we divide it by 7.3 times 10 to the minus moles of sucrose. That's going to give us our delta H. One thing that we need to pay attention to is it going to be a positive or negative? Negative. Because it says produce, right? So negative. Basically, we'll have a negative, whatever value you get. So where's the negative? We got the negative because we know that it was being produced, right? If you read the question, it says, worth 43.7 kJ of heat is produced. Okay. Questions? Okay, so Victor, you gotta cook something. Sorry, cook something. I'll
That's
bring the I'll bring the cutlery, 'cause I already have a lot of it. And I have the napkins, and napkins are ready to go. So you gotta cook something. Man, me and Chocolate Planet, a couple of places. Determined who's the best. So I got cups. I have cups, plates, and cutlery already covered. I have it back there somewhere. So. I suppose it's good for something. Okay.
Yeah, I know that's.
I love they sit there and they argue about it. No, I got this. That's good. Yes. did mean it. So I wrote down the wrong number. It's 7:44. Okay, so then I wrote down the wrong number on my page. This next. So then that would change your answer, right?
Yeah.
What did you guys get? I'm just keeping you guys up to toes, right?
I wrote it. No.
Well, that's if you just cross it out. Put your initials. What did you get? What was the value?
Negative 5,000.
5,961. 28. So then we know that. Looking good already. Good. Let's get a lot of desserts here. Ooh, mashed potatoes and gravy.
Yeah. Everybody's gonna be something from that.
Everything was. Pizza. Oh, you said pizza. Pizza is always a safe go-to.
Oh, for sure.
Is it gin and tonic? Gin and
No,
tonic
no,
works
no, no,
too.
no. I'm lactose intolerant.
Oh, okay. Okay, okay. How you guys feeling so far? Not too bad? Okay, so we're gonna take a break and then we'll come back, because I told you today was gonna be all day lecture, right? Hey, how are you? A little late.
I know, it's forever.
How's your teeth?
I can't fit my mouth.
Okay, so let's go ahead and take a break and then we'll come back, finish up. Finish up where we can finish.
I'm trying to go horse. I remember being able to go horse.
And having some difficulties with.
It's for that Halloween piece.
With this classroom,
Are you trying to get a style or are you trying to get like realistic horse? No, no, hell no, realistic. If not, it's gonna end up with that 40-year Christmas.
Yes, sir. She got started.
Oh my God, there's another one.
Yeah, I know. Hello.
Even if you are going for sort of freestyle, it's just like in the head of it. I was thinking of the big ass heads. No, yeah, their heads are big, but they're not wrestling bodies. They're still pretty sensible, but I'm like, I'll figure it out. Their heads are smaller than their cheeks. Like, you know, bad. I just want to like flip their canvas. Shrink their head.
Can you order like, I'll send it like, I have because some people catch on.
Then you can swap apps. Probably don't add apps. There are no specific apps that are good. Even if it's just gonna use some, no, they really just take a place. What would you want more? This package.
Okay, standard state. Okay, so we kind of talked about standard state sort of already. So standard state basically means pressure of 1 bar and a solution at 1 molar. Okay. The way that we signify standard state is using the not, the 0. Do you guys have a question?
That's all like they're like plastic. Cause it says top, so I think they're not. Ah,
So these are
yeah, these are the little, it's like a little organizer, but this is like
you actually just have a divider.
this. Yeah, but I was like, I don't know what this is, and I don't know what that is. I'll just clean them up.
That is probably some type of. That's my first. Okay, so back to not. Not basically the way that we signify those standard state is by using the not. So you'll see the symbol delta H not, and then that'll be the temperature that has been signified. So the 298, which is typically. Okay, questions? So why is this important? How many of you guys have your phones available? How many of you guys have access to OpenStax? OpenStax on your phone? OpenStax is where your book is at. Yeah, so you guys can actually go, if you guys go to OpenStax, go to your chemistry, and it's E2, that's the new edition, the new edition. I'm sorry, 2E, I said it backwards. Or if you have your book, you can go to the appendix, appendix G. It'll be in the back. Appendix G. So let me see, I'll go do that myself, so you guys can see it on my end. Appendix G. Okay, if you guys go to appendix G, so that delta HF, so that's delta H formation. We'll talk about that here in a minute. That is going to be essentially where we're going to have our standard state enthalpies located. So we're going to use this to sit there and determine our enthalpies, right? And I'll talk to you about formation, delta H of formation here in a minute. Okay. So when we always talk about our delta H is always going to be normalized with per mole basis. Right? So it's going to be made based upon per mole. So the enthalpy of standard state combustion, it'll often be written as delta H not C, or sometimes it'll just have combustion written at the bottom. So that just basically means the heat of combustion, right? It's also this symbol for the heat of combustion. Okay, so for example, if the enthalpy of combustion of ethanol is negative 130, negative 1,366.8 kilojoules per mole, then that basically means that, let me write this equation. Basically means that for every 1 mole of ethanol, this is how much heat is going to be generated. Right? So, like I said, it really means per mole of ethanol because it's based upon whatever is being combusted, the important feature of the reaction. Like in the other case, remember it was water. So it was based upon 1 mole of water, 1 being the coefficient that was in front of it. That's kind of understood. Does that make sense? So here is some of the, this is just a small table of the same stuff that you guys are going to see. Although these are all for combustion.
Okay, I didn't see that page on here, because I looked at the table of contents, it gave me specific page, but it doesn't go back.
It doesn't go to delta. It's because there's 2 volumes. All of the appendices are in the 2nd volume. So what you could do is go, if you go to Mesa, they'll do the 2nd. Tell them you need to say, I'll type some that you need to say. Yeah, that was the bad thing that when they bought the book, they bought, said it bought, because if you look at the book, it's also not in color, right?
Right.
Just kind of, it's not in color and it's split up into 2 volumes. Okay, so here again, just more examples. Okay, so it says, as figure 5.10 suggests, the combustion of gasoline, okay, let us determine the approximate amount of heat produced by burning 1 liter of gasoline, assuming that enthalpy of combustion of gasoline is the same that of isooctane, a common component of gasoline. The density of isooctane is 0.692 grams per liter. While you guys look at that, board. That reminds me, I look up here. If you guys have any stuff that you guys want to keep for ESL that you guys have back there, or we have everything back here, let me know, come pick it up, and then anything that isn't kept will either be, I mean, that you guys will take with you, will either be packaged up and saved for next year, or so. Okay, so these are the things that were given to us. Okay. So how am I going to use this solid line? What is the one?
Determine the heat.
So we're looking for Q, right?
Yeah.
Okay. So where am I going to start at? It is. Okay, wait. Let's see. We're going to use this chemical equation. So what's given to us? Molar mass given to us?
Was that ML? Like,
Oh,
a liter?
yeah, so that's this. That funny side, that's symbol, that's rho, that's the standard symbol for density. Density of gases.
So we have density.
So what is this first part? That's what volume. Okay, so why not start with that volume? We have 1 meter. 18. So we want grams, right? Because we need to get it to moles. So how can I get my density? I mean my volume to grams. How can I? Any hints there? This mass, mass, and that volume. It's another way of getting this mass. Okay. So, but first, this is liters, right? This is milliliters. How do I go to
So you go from
Divide
liters.
by 1,000.
divide by 1,000? Or I say multiply that by 1,000. 1 liter, 1,000 milliliters. Now, then we can use our density, right? And so then we have 0.692 grams. Okay, so how can I get to moles? Molar mass, that's right. So we're going to use our molar mass. We have 8 carbon, 8 times 12. And we have 18 hydrogen, 18 times 1. Here we got measured from line.
Yeah.
We haven't got it yet. It's 150.
14.
Oh, and here's the beauty part, right? So we know that this is kilojoules per mole of HPT. So since we have moles of that, to get how much heat that we're generating, just multiply.
But it was just a triangle or
It
it
was
is?
not supposed to be a triangle. Trust me now.
Oh, I see. Let's see.
I did this one.
Let's see.
Was that?
No,
Say, Dr. Can you?
no, no, no. Not at all. Thought it was like something squeaky.
Yeah. How many sig figs should I have? How many sig figs?
Three.
Three. Yeah, it's not. 33,000.
Yeah. It's not good.
Negative means what?
Extra. Really expensive.
Yeah.
Right.
Oh, yeah,
It's six
put it in.
more.
Negative 561.
Okay, questions? No questions? Sorry. Cash delay. Okay, guys, ready for the next part? Almost ready? Everybody got it down though? Okay, so an example is like the energy that's going to be used by biofuel. So in industry currently, a lot of jet fuel or part of jet fuel is basically used by biodiesel. So they make biodiesel by using organisms such as algae and bacteria, and they'll grow them in these culture bins, and then they'll harvest it, and then at the end of the day, when they harvest it, they'll synthetically make biodiesel. When they then make biodiesel, they'll actually do that extraction. And then from the biodiesel that's been harvested, that's been generated initially, then they'll process it even further and get it purified, and then they'll basically use that for jet fuel. or diesel. If you guys stay with me long enough, and you take OChem, you guys will be making some biodiesel. Hopefully, we'll have a car to test it out. That's our goal with our 3D printer. Okay, so now if we look at the enthalpy of formation, delta HF, delta HF just basically means that we're making it from the raw elements. Okay, so in this case, we're making it from carbon and oxygen, in the case of carbon dioxide. Okay, so you'll notice that formation is going to be made from your elements initially. So we have carbon, and then we have oxygen, and then we make carbon dioxide. These are those raw elements. And then this is the enthalpy of formation for those. That's how much energy it takes, or that's how much energy is going to be released for that formation. Which is pretty good if you consider. Now, what I'd like you guys to do is write the enthalpy of formation, or write the formation equation for ethanol and calcium phosphate. I know it's written up there, but it wasn't supposed to be. Probably didn't even notice that until I said something, right?
Yeah, we never said anything, I'll just try to.
Let me help you out. There we go. Does that help? I know, it's still on your paper. Okay, so the idea is that we'll give you a different one here. We'll give you a different one. Guys, I make so damn hard. Okay, so let's see. Let's do isopropyl. C7. And we'll do ammonium hydroxide. Awesome. Yes, let's get rid of this. Yeah, let's get rid of it, because you guys don't want to do it. Well, next semester.
So next semester, what comes in?
Sorry. Was that?
I'm not gonna be here.
That's right, when you come to visit, I'll put you there.
That's my time to go.
That's right. But you know, what better way to do it than at work, right?
Remember the good old days.
Yeah, exactly. Reminisce.
Sure. You want to put it there back in the kids?
Yeah, anything that is left. Okay, everybody got it? Okay, let's start with the first one. Okay. So what would be the chemical equation? Is that going to be a solid, liquid, gas, or gases? Carbon's natural state is graphite. Graphite is solid. Think about your pencils.
Yeah.
Okay, plus 4H2 plus half of 2, half O2.
Yeah.
It sounds like you said half of 2.
Oh.
And that's going to make propanol, right? H7 OH. My funny looking thing.
Also, I'm asking, is that you?
Explain why carbon is a solid, not a gas.
Because
Same question.
carbon's natural state is graphite. By room temperature, carbon is always going to be solid. What was that? Yes, you have carbon right there, graphite. Yeah. Is it gaseous at room temperature? So you want to think about what it is going to be at room temperature. What was that? Yeah. Is it not? Is graphite not a solid? It is. And then what about oxygen? Oxygen at room temperature. It's a gas. And then hydrogen. Gas. At their natural state, yeah. At their natural state, at room temperature. 298 degrees Kelvin is the same thing as like. What was that? The 4H2?
Yeah.
Sure, because if we look, there's 7 hydrogens here. And then there's 1 additional, so that's a total of 8.
Oh.
Okay. Now we're going to put the ammonium up top. Okay, so ammonium up here. So it's going to be the chemical equation.
Because I'm always wrong.
No. Not always wrong.
You got some right for it.
Yeah, you have.
Everything is.
It's like blind faith when you answer some questions.
Well, see, that's the problem.
I mean, you're the one that's been getting away with the.
I feel like it's just supposed to be an end, but I feel like that's.
So what do we know about nitrogen?
I cool.
Oh, okay, so what does that mean? Was that, how's that significant to us? What are we, just alcoholics or what?
Yes. No, it's all right. Yeah.
diatomic, so those are the diatomic.
So it has two, so it's only two in.
Okay, so we need N2,
Yeah.
okay, and that's solid, liquid, or gas.
That's liquid, right? No, don't get me wrong. So I know it's it has a solid. It's a gas.
But how do we
Right.
check, on the element, whether or not they are,
If you look on the periodic table, your periodic table tells you so many important things.
Yes.
What does it say?
It's a red N.
It's a non-metal, that's true, it's a non-metal, but it's also the gases.
Yeah.
At standard.
Yeah.
So if you look at, what was it, mercury?
Oh yeah, it's a special piece.
What is it, what does it say on it?
It's blue mechanical.
We have
And what
one
is
line,
blue?
yeah.
Mercury. Liquid.
Oh, so that's what all of the different colors are. Yeah, it's color coded.
Yeah, it is. Unless it's already.
So, what else do we have?
So there's.
What are gonna be, give me the elements that we're gonna have to get. So we have nitrogen,
Here's where I got stuck.
oxygen, so
Yeah.
that's O2, right?
Yes,
That's
sir.
a gas. And hydrogen. Okay? So how many hydrogens are we gonna have? We're gonna have 5.
Yeah. No.
Oh, wait, no, two.
It's gonna be H2, yes, but we're gonna have the coefficient.
It can't be three.
Can't be 3.
How do you get a 5? I mean, you're multiplying us through.
What times 2 would be 5? 2.5, which is
Yeah.
5 halves, right?
Yeah.
We'll just make it as a fraction, 5 halves.
See, I didn't know those.
Did you guys see me do it down here?
Yeah.
Well, I was just.
That one makes sense. So like, that
Oh,
one.
you can do it for everything, right?
Look,
He
that
is-
one looks
the
like.
key is so that you have 1 mole, 1 mole of the thing that's important. So we want 1 mole of this guy. We're setting it up so it's always 1 mole of whatever element that you're making, whatever element that you're making.
So we don't have to do fractions still.
That's,
Reactions.
that's right. So it's so that we can always end up with 1 mole of whatever's. It's in the formation. Okay, how many oxygens? What is that? 1/2. And then how many nitrogens? 1/2.
Yeah.
Well, we got carried away with the halves there, didn't we? Okay, questions? Questions, no questions? That's right, only for enthalpy, yes. I hear that so much. I hate fractions. Okay, any questions? Concerns? Cash, Kool-Aid? Okay, questions? Report. That's right. You want it to be 1 mole of that, because everything is going to be based upon 1 mole of what's being. Okay.
I wasn't gonna struggle. So.
Okay, so the next thing that we want to talk about is Hess's law. Remember when we were talking about that concept of a state function, right? So Hess's law is just going to be applying the fact that that we're going to use state functions. Okay, so let me kind of explain to you a little bit, and then I'll go into a little bit. So first off, there are a couple things that you need to know about enthalpies. The way that we determine enthalpies are two ways. One of them is we measure it experimentally, so we measure it on the spot experimentally. That's one way. The other way is that we calculate from other experiments that have been used to determine it. And you can use like a couple of equations to sit there and build up to that particular one. Okay, so and I'll show you an example. Okay, so in all honesty, it's really, really hard, particularly with the instruments that we have in our lab. We'll say definitely with the instruments that we currently have in our lab, right, to measure the enthalpy, right? So because of that, our best bet, we want to try to get as close to the correct answer as possible, is to actually use what's given to us in table, G, appendix G. The piece of information in appendix G. Okay, so and to do this, we actually have to use Hess law. Hess law basically says that we can add up several equations as long as the end product is that equation that we want. Let me give you an example. Okay, so let's say we are trying to get to carbon plus oxygen makes carbon dioxide. So that was the enthalpy that we wanted to try to figure out. So one way is that we could sit there and figure it out with just this that we have right now, right? So we can look up the heat of formation this way. Or we could actually do it by a two-step process, or a three-step process, or a four-step process. So in the case of a two-step process, we have these two equations, right? The very first equation makes carbon monoxide. And then we use the fact that that makes carbon monoxide to make carbon dioxide, right? Now, if you look at these two equations, if we add the equations together, we add up what's on both sides of the yield sign, right? You end up with this down here, right? So it's just adding the two sides of the equations together. Now, if we do that, and we pay attention to what's on both sides of the equation, like for instance, we have carbon monoxide on this side of the equation, and we have carbon monoxide on this side of the equation. So since it's on both sides, like product and reactant sides, it's going to cancel out. Spectator. Okay, so then at the end of the day, and then we add these two oxygens together, 1/2 plus 1/2 is going to be what? Oh, right? So we add those together, we end up with C plus O2 yields CO2, right? So this is two steps. Now, since we have those available, it's easy to do. We add these two together. We add up both of these together, and they should add up to approximately what we get. Okay. And if we add these up, that should be 394. Minus 394, right? For our delta H. This is the sum of the two. Okay. So if we look back, what do we have for negative 394? If we just went directly there. So in other words, this here represents the full enthalpy. So if we take the enthalpy for one reaction and then take it to get to that other reaction, it should all add up to the same. Right? Basically what we're saying about the mountain, right? So if I go up this way, I'm going to use the same amount of energy as if I go up this way, right? And then if I fly up, but it always end up being the same time. Just the different steps. One, we took multiple steps to get up there. We took a path to get up there. One, we went straight forward. Okay, does that make sense? A little bit. So it's kind of like math. If you want to just look at it mathematically, if we look back at the equation, we look back at this equation right here, right? So all it is that if you have this, have you guys ever added two equations together? Right? It's that same concept of adding two mathematical equations. Things that are on one side of and the other side. Okay, now if I have them on both sides of the equation, I can cancel it out, right? So it's going to be exactly the same concept. Instead of having an equal sign, we have to use. Okay. So now the thing is that one thing we have to keep in mind is that the orientation of our chemical equation. So remember, our chemical equations can be flipped back and forth, right? So sometimes we need to flip it to go in one direction compared to the other direction. Okay. And so because of that, this is the way that you're going to set up your equation. This is the easy way of remembering how to solve. Okay, so delta H is going to equal the sum of the number of moles multiplied by the heat of formation. And then that's going to be the sum of all your products. Okay, so you're doing the products first. And then you're going to subtract the number of moles times the heat of formation of all your reactants. Okay, so here's an example. It is not the best example because you can't find all of our enthalpies in appendix C like they said they could. I looked, there's a couple of them are missing. I think one of them is missing. I think it's actually the first one. But what you would do in this case, so the enthalpy of formation here is for nitric acid is going to be negative 207.7. So then you multiply the coefficient times that value, right? Those moles cancel out. Then you're going to multiply, add the coefficient multiplied by the heat of formation of nitrogen monoxide, since those are your two products. Okay? So then you're just going to add those together. That's going to be the sum of those. Okay. Then you're going to subtract the sum of the heat of formation of your reactants. So then that's the heat of formation of the nitrogen dioxide. And so that's 3 moles multiplied by this value. And then 1 mole of water multiplied by the value. How you guys doing? So should I give you guys a real life example? That help? So let me pull together something. What was that? So let me pull together something. Okay, so let's say we have There it is. What's that?
Other stuff that doesn't relate to chemistry.
Okay, so let's say we have this chemical equation. So we know when we balance it, first off, we're gonna have to balance it. So then it's 1/3 here. Is that true? Yeah, I know, maybe.
Yes.
Okay, so since we know that this is gonna be the case for that, okay, so then what we're gonna do is we're gonna go to appendix 2. Everybody got the chemical equation written down? It's balanced, right? So. We have. I'm gonna write on the sides, so that we keep it. So O3 gas state, our delta H is gonna be 142.7 kJ. So then beryllium. Okay,
Another 7. 142.7. Okay.
Okay, so for beryllium, we're looking at beryllium gas. G. Is going to be delta H. 4.3. Okay. Then for beryllium oxide, that's going to be H equals negative 609. Okay, so we're going to use this. Okay, so it's the sum of the products. Right now we only have one product. What is the coefficient that we have in front of that? 1. Okay, So then we have 1 times the value of our delta H. That's right, and that's negative sign. So it's negative 609.4 AJ kilojoules per. Okay, and we know that this represents 1 mole. Everything except what I want. Why don't I just okay. And then we're going to subtract, and it's the sum of both of my product both my reactants. Okay, so coefficient that we have in front of the E, 1, so that's 1 mole, times that delta H, which is 324.3 KJ. So again, those are going to cancel out. Then we're going to add. In this case, we have 1/3 times 2.7. Okay, so you're going to get equals 9. Negative value. That's KJ. And then in this case, this is going to be per mole, per 1 mole. of our B. Okay. So that would be our enthalpy for this. Okay, you guys see that? How your brains? A little squiggly.
Makes sense.
How's that?
I'm still writing it.
Still right.
That's not bad.
Yeah, it isn't. It's just addition and subtraction.
Yeah.
And simple multiplication.
Because I don't know how to plug it on my phone, so I got to run it. But it makes sense. Like I followed through it makes sense. Like I understand the process. It's just
Okay.
the iPhone's complicated.
Okay. We got to work on that, right?
Yeah. I missed my old tech. That one was fixed. That one was easier.
So the hardest thing to remember is that you have to multiply it by the coefficients. Right? Once you get the enthalpies for each shiver and everything, you have to multiply by the coefficients.
So we did 1/3.
Yes, but then that means that instead of you divided by 3 moles in that case, right? Because you're saying that you have 3 of them. That's right. You want it per. Yes, per. Yeah, you always want it, enthalpy is always, you always want it written as something per 1 mole. Okay, questions? No questions. Did you get it all written?
Nope.
You say yep or no? Yes. Oxygen? Because I have 1 oxygen here, right? I know that there's 3. 3 times what is going to equal 1? And that's by 1/3, right? So that's what I did. Yes, and so technically you could go through and balance them all, but then you're going to have to divide it by 10. Okay. Good. It's like zombies.
I've been a zombie for 4 months now.
What was that?
I've been a zombie for 4 months now.
Oh, really? For a full month now?
I'm assuming that's how long it's been since I had a vaccine. Yes.
Okay. I thought you meant about eating grains and everything. So I was like,
Too
huh.
squishy.
Okay, so let's go to chapter 6. And we'll start chapter 6. We'll only do a little bit, and then I'll let you guys out early. We get out at 5, so we still got. Okay. And we did take a long break.